All right, so as Ray Stevens said, he was his own grandpa, and of course that song is just to help us remember that e to the x is kind of like his own grandpa, if grandpa means derivative, right? E to the x is his own derivative. So what's the derivative of e to the x? E to the x, yeah, e to the x is its own derivative. Pretty cool. Now, you're not going to just have e to the x floating around there that often. Most of the time, we have a composite function as e to the blob. So if you let u be the blob, that is a differentiable function of x, then the derivative of e to the uth power becomes e to the u itself times u prime. That's the chain rule built in to the rule. So let's try it out on example 2. It says find dy dx if y equals e to the x plus x squared power. So you got e raised to the blob power. So the left side becomes dy dx. And on the right side, we got the derivative of e to the blob, which is e to the blob. And then times the chain rule back on the ground floor out of the exponent times the derivative of the blob, which is 1 plus 2x. Yeah. And that's it. You're essentially done with the derivative. If you wanted to put that other term or that other factor first, you could. Or if you wanted to distribute the e, you could as well. So whatever. Just rewriting it. But that's it. So we'll get a chance to practice that quite a bit. One of them is good enough for now. Now, what happens if it's not base e? Because there are other exponential functions out there. So what we're going to do now is we're going to figure out, like for 2 to the x, if we were to actually graph 2 to the x, it would look very, very similar to what e to the x looked like. The only difference, because e is 2.718, and of course 2 is 2, the graph of 2 to the x for positive x values would be where in relation to e to the x? Would it be above or below? Yeah, below. 2 to the x is 2 is smaller than e. So it would grow, but not as fast. But if I were to do the qualitative analysis on it, then I could kind of make the same qualitative claim that the graph of 2 to the x is going to be very similar to itself, if not exactly the same. So could it be that the derivative of e to the x is e to the x, and the derivative with respect to x of 2 to the x is 2 to the x? That could be, right. Qualitatively, there's no way to know if it's not. So that's where we're going to go to the calculator. I'll put a question mark right there. We're going to go to the calculator and let the computer figure out what it is. So all I have to do is go to y equals and change my y1 to 2 to the x. And it's already set up in y2 to just graph the derivative. So the blue is 2 to the x, and the red is the derivative. Let's see if the red covers up the blue like it did for e. Red, blue, red. Anyone still see the blue? Yeah, I do too. Yeah. So it appears that the derivative of 2 to the x is not itself, but it is another exponential function. You could look at the blue and maybe think about how you could adjust the blue graph to get the red graph by some kind of transformation. Because it's lower, it looks like it's going to be some kind of vertical compression. Would you agree to that? If we take the blue graph and vertically compress it by some factor, then maybe that could give us the graph itself. So it's not itself. Let's come back over here and say maybe, though, it is something times 2 to the x. And because the derivative graph was below the original function, I know that a has to be between 0 and 1. Remember, that means it would be a vertical compression. So does anybody have a guess as to what that might be? Very good. 1/2 is a great guess, Katie, because 1/2 is less than 1, and it also has a 2 in it, right? So let's try that out. Let's try it out. I'm going to come down here to, we'll go to y3. If I go ahead and sketch 0.5 times 2 to the x, maybe that will cover up the red graph. Let's see. Yeah, no, it didn't. So compressing it by a factor of 2 with an a value of 1/2 compressed it too much. So it has to be, so we're going to have to compress it, but not as much. So let's try, instead of 1/2, let's try 0.75, which of course would be 3/4. And I'll insert a multiplication symbol there. Now let's see if the black graph covers up the red one. Ooh, now we didn't compress it enough, right? So I know that it has to be somewhere or between 0.5, which was compressing it too much, and 0.34, which wasn't compressing it enough. So any idea what it could be? Let's try, 0.70. Let's try that. Not bad, not bad. I can still see little pieces of the red graph. If you go to the table, you can see 0.693 and 0.7. They're not even necessarily the same in the first decimal place, but that's close. So let's try like 0.69. Try that, and that looks really good. You can still see a little bit of the red sticking out there. So if you go to the table, it's a lot better. 0.54 and 0.52. So we're on in the first decimal, but not the second. So now we can maybe try adding something back to it. I'm gonna maybe 3. 0.693. Yeah, let's see if that works. Oh, that's getting better and better and better. So here's what we could say. We could say that the derivative of 2 to the x is some scalar multiple of itself, which would be somewhere around 0.693-ish. Okay? We'll figure out why that is right now. Right now. We can actually figure out what it is exactly if we use this little idea. If we can write 2 to the x as a power of e, we've got it. Well, e to the natural log of x is x. That is an important little property. E and ln are inverses of each other, so when you compose them back to back, you get what we started with. That means we can write 2 to the x as e to the natural log of 2 to the x power. Do you agree? Good. And now, because there's an x on the 2 in the exponent, we could bring that out front and call that e to the x times the natural log of 2's power. Which now, with a little bit of commuting, the natural log of 2 is just a number times x. Now we could take the derivative of 2 to the x by taking the derivative with respect to x of its equivalent, e to the natural log of 2 times x. And we can do that because now we know the chain rule for e. We have e to the blob. What's the derivative of e to the blob? Itself, right? Itself. So e to the natural log of 2 times x times the chain rule. What's the derivative of the natural log of 2, the number, times x? Just the natural log of 2. Yeah. And now we can kind of rewrite it. What is e to the natural log of 2 times x actually equal to? If you look at the line above, remember it's equal to 2 to the x. So we can write the derivative then of 2 to the x to be 2 to the x times the natural log of 2. And of course, the natural log of 2, if you type it into your calculator, is about 0.693. So Katie was right with her crazy out of the blue shot in the dark guess of the natural log of 2. It is related to the 2. In fact, this 2 right here came from that 2 when we wrote it as the power of e. So maybe now we can project, based upon that, what do you think the derivative of 5 to the x will be? Itself times natural log of 5. Yeah, well, let's see if that's correct. We could verify that now on the calculator. Coming back to the calculator, let's change this one to 5 to the x. And then I'll come down here and I'll change this to the natural log of 5. And I'll delete that. So if it is, it'll graph the blue function, then the derivative by computation. And I need to change that to 5 too. Thank you. And then the black graph should cover up the red graph if it is, in fact, the derivative. All right? It is. Very good. Yeah, so notice the derivative of 5 to the x is actually bigger than the original function. So this would have to be vertically stretched by a factor bigger than 1, and it turns out that the natural log of 5 is bigger than 1. It's 1.609. So we have now kind of proven without using variables, we've kind of verified the following. The general derivative of any exponential function of the form b to the x power. Now we have values for b that work. B has to be greater than 1. If so, it's a growth function. Or b, the base, has to be between 0 and 1, in which case it's a decay function. But anything of the form b to the x then is going to be itself, like e to the x, times the natural log of the base. In general, the derivative of any exponential function is itself times the natural log of the base. And that should work for e to the x as well. Watch this. The derivative with respect to x of e to the x, by this new rule, should be itself, right, times the natural log of the base. The base is e. What is the natural log of e equal to? 1. And because the natural log of e is 1, e to the x is the only exponential function that is its own derivative. Because the natural log of any other number is not 1. That's kind of cool. E to the x is the only exponential function that is its own derivative. Everything else is a vertical stretch or compression of itself. Now, of course, we can work the chain rule right into it. So this would be the most general rule you could have for exponentials. The derivative of b to the uth power is itself b to the uth power times the natural log of b, and then times the chain rule. The derivative of u is u prime. Chain rule built in. All right, so let's do a couple of examples. Example 4, here's a nice application. At what point on the graph of y equals 2t minus 3 does the tangent line have a slope of 2? So what's our plan of attack here? The tangent line needs to have a slope of 2. That means that the derivative of y with respect to t better equal what? 2. So there's your strategy. All right, so I'm going to need the derivative of y with respect to t. So the left side is just dy dt. And here I am faced with the derivative of 2 to the tth power. How do I know that's even exponential? Is it t times 2 to the t minus 1? How do you know not to use the power rule there? Yeah, right. Power rule is when it's flipped, when the variable is the base and the number is the exponent. This is exponential when the number is the base and the variable is the exponent. So it's not the power rule, it's the exponential rule. So it's itself times the natural log of 2, the base, and then the derivative of negative 3 is 0. So now I can set that equal to 2 and solve for t. So if I do that, I'll divide through by the natural log of 2, and I get 2 over the natural log of 2. Ruh-roh. How do I get t now out of the exponent to solve for it? With logs. Yeah, we could take log base 2 of both sides, but in this class we pretty much just use the natural log. So I'm going to take the natural log of both sides. That's a little pre-cal. Going back to pre-cal. So now with the natural log in front on both sides, on the left side the t can come out front and becomes t times the natural log of 2 equals the natural log of 2 over the natural log of 2. And now I'm almost there. The natural log of 2, remember, is a number. It's about 0.693. You divide through and you get, for your final answer, the natural log of the quantity, 2 over the natural log of 2, all over the natural log of 2. Does any of that divide out? No. Now, there is one thing else we could do to make it look less complexy. Remember, the natural log of a divided by b is the same as the natural log of a minus the natural log of b. The log of a quotient is the difference of the logs. We're going to study kind of logs again in the next section, but there's another property. That means you can write the numerator now as the natural log of 2 minus the natural log of the natural log of 2 all over the natural log of 2. And again, nothing divides out, unless you want to split up the terms and call it 1 minus, but I'm just going to leave it like that. So this is the exact answer. Now what I want to do is verify it. If you look at the graph of 2t minus 3, that's your graph of the function 2 to the tth power. It's moved down to negative 3. It's got the horizontal asymptote down there, and then it looks something like that. And I want to know at what value of x is there a slope of 2? Right there. So somewhere in there. So let's go to the calculator and verify that we did it correctly. The first thing I'm going to do is type in my final version of what t ended up being. So alpha y equals, I'll use the horizontal division bar. I get the natural log of 2, close parentheses because it opens it automatically, minus the natural log of 2, and then close, all over the natural log of 2. So that gives you 1.528. So we had the exact value of that. Pretty neat. Now we can verify it. I'm going to store that as alpha A. Store that as alpha A. And remember, we could take derivatives numerically on our home screen. Math 8, I'm going to take the derivative with respect to x for my function 2 to the x power minus 3. That was my original equation, right? And I want to compute the slope of that at what I stored as a. So I can just hit it alpha A. And if the calculator is correct, I should end up with what? Remember what we were trying to do? We were trying to figure out where the slope was? 2. So if the calculator is worth having as a tool, it should tell us 2. Stupid. It doesn't tell us 2, does it? Or is that the calculator's way of saying 2? That's the calculator's way of saying 2. And if you don't realize that, be careful who you're calling stupid. Okay? Calculator may not have ears, but it also doesn't have feelings. So I guess you could call it stupid. But it's only as smart as the operator, the person behind the keys, or in front of the keys. It'd be hard to type if you're behind the keys. Right? You have to be like really small and inside, I guess. So that's pretty close to 2. The calculator, when it finds derivatives, is not using exact numbers. So that is a very good indication that the answer is 2. All right, you ready for some rapid fire practice? Example 5. Example 5. We have A, B, C, D, and E, and we're finding the derivatives. So what we're going to do is possibly rewrite so that we can take the derivative. Now, is this going to be the power rule? Let's find out. The answer to that is no. Because you have a numeric base and a variable exponent, that's an exponential factor. So it is going to be the exponential rule. Because the exponent is negative 3 divided by x, I'm going to write it as negative 3 times x to the negative first. Because I'm going to have a chain rule to do, and when I use the chain rule, I'm going to have to take the derivative of the exponent. Now it's written in power rule format. So here we go. Any exponential function is, first and foremost, itself, right? But because 7 is not e, we must multiply by the natural log of the base 7. So that takes care of the new exponential part. And then times the chain rule, the derivative of negative 3x to the negative first, you get positive 3x to the negative second. Now, 3 of those, or actually 2 of the 4, have negative exponents. So if you wanted to clean that up, you could say it's 3 natural log of 7 all over x squared times 7 to the positive 3 over x power. That would be one way to clean it up. Kind of looks nice like that. Now you could also do this. You could bring the 3 up as an exponent on 7 and call it the natural log of 7 cubed. But that kind of goes away from the spirit of logs. Logs are supposed to make molehills out of mountains, not mountains out of molehills. And that would make that number much bigger. So I probably would not do that. College Board would not really do that. But I will tell you this. College Board loves to play with logs. So if there's a log expression, as you'll see in the next section, we're going to get used to kind of manipulating it at the end. All right, any questions on A? Now we're on to B. How rapid fire was that, right? Like musket rapid fire. All right, this one is the derivative of e to the natural log of x. When should we simplify? Late never? Early and often. Right. Now you could take the derivative of this using the e rule. The derivative of e to the blob is e to the blob times the chain rule, the derivative of the natural log of x. Have we learned the derivative of natural log of x yet? No, that's a log function. That comes in the next section. Should we jump to the future? Nah, we don't need to do that. Because what is e to the natural log of x? What does it simplify to? X. Now this makes a fantastic multiple choice question. Guess what answer choice A is going to be probably? X, for the person who's like, ooh, I recognize e to the natural log of x as x. But we haven't really taken the derivative yet, right? We haven't busted out the calculus, which is why notation and syntax is so important. The d dx is still there. What's the derivative of x? 1. So don't be that person that misses a super easy one, the derivative of x, just because you get so excited. On the one hand, I understand it is math. It's easy to get excited. On the second hand, you need to show a little bit of self-restraint. All right, this one here, you walk up to the problem and you're like, what's up, blob squared? All you see is parentheses squared, so it's a chain rule. So the derivative of blob squared is 2 blob to the first. And you get e to the negative teeth plus e to the positive teeth. Times the chain rule. 2 terms, you get in the habit of putting dot parentheses, or just parentheses for the chain rule. What is the derivative of e to the negative teeth power? Well, it's first and foremost itself, e to the negative teeth, times the natural log of e if you want to put that. Do we need to put the natural log of e? No, because that's 1. Times the chain rule, the derivative of negative t, which is what? Negative 1. For some reason, people miss that. When the exponent or the inside function is more than just a plain old single variable, there's going to be a little chain rule. And then plus the derivative of e to the teeth power is e to the teeth. Now that's funny. If someone walked in right now that didn't know math, they would think that we forgot to take the derivative of that second term. When in fact we did. It just so happens that it's its own grandpa. You should have been here earlier. Don't walk in late and start judging. Be here for the Ray Stevens song. All right. Now I'm going to flip the terms around in the first factor. I'm going to call it e to the t plus e to the negative t times e to the t minus e to the negative t. And the reason I wrote them like that is because now you can clearly see that these two guys are related how? When you expand them, you get a difference of squares. Very good. Because those two guys are what you get? Conjugates, yeah. Just want you to be aware of that. You don't have to expand it, but you do need parentheses. Okay. All right. Okay, good. Expand them if you want. Let's do it, as Katie says. E to the t times e to the t, is that e to the t squared? E to the 2t, very good. Because you add the exponents, t plus t is 2t. And then the inner and outer cancel it. You're going to get a 1 minus 1. How do you get a 1? E to the negative t times e to the positive t is e to the 0, which is 1. But you get a 1 minus 1, those cancel. And then you're left with minus e to the negative 2t. Very good. So that's just doing a little bit of extracurricular at the end of the problem. All right, letter D. Oh, my gosh. Okay, we have a product of 2 variable functions. So it's going to be the product rule out of the box. The second factor looks kind of intimidating. So I'm going to go ahead and take a line and rewrite it, if for no other reason but to delay the inevitable, me having to differentiate it. I'm going to put x squared in parentheses. Now, the second factor I'm going to rewrite. How many layers do you see on that one? There's actually 4. And most people, if they're going to mess it up, it's because they don't see the first or the second layer. You have a 5 raised to the blob power. That blob then, the next blob is blob squared. And that's what some people miss. And then you have the sine layer, and then you have the innermost layer. So don't be reluctant to write condensed trig expressions or log expressions, as they are sometimes written, in expanded form when you're evaluating it or when you're taking the derivative of it. Okay, so now I've rewritten it. That should help me be successful. So start over here a little bit more to the left than usual. The derivative of x squared is 2x times the second factor. I'm just going to rewrite it, and I'll rewrite it back in its condensed form, sine squared of 4x. There's the first term. Plus, now we just rewrite x squared, and the derivative of the second factor, that's exponential, because it's a numeric base and a variable exponent. So the derivative of 5 to the blob is 5 to the blob times what? The natural log of 5. Please don't forget that. That takes care of the exponential piece. Now we go inside, and the next layer is blob squared, and this is the one people miss, 2 blob to the first, times the next layer is the sine layer. That's going to be cosine of the blob. And then the innermost blob is 4x times its derivative is 4. And then I didn't put all that in parentheses. I should have done this. Let me erase that one. Put a dot, and then I'll close that one. There we go. Now, you could simplify that if you want. A lot of these exponential derivatives are really good for factoring after the fact because they do produce themselves as part of their own derivative. You'll have a common factor in both terms. So you could factor out the 5 to the sine squared of 4x. One other thing to bring to your attention, because it came up as I was working the key, remember that right there, that and that alone can be written as sine of 8x. Good. So always be aware of the double angle identity for sine. It shows up quite a bit. 2 sine of blob cosine of blob is sine of twice the blob. So that's the double angle identity for sine. That kind of cleans that piece up kind of nicely. But I'm not going to clean anything else up. The purpose of this one was just to unpack the boxes using our new rules. Of course, the chain rule is always there. And then we get to the last one, E. So let me kind of shrink this down so we're not encroaching on the space. What rule are we going to use for this one? Exponential rule, product rule, power rule. Yeah, E cubed is not a variable term at all, or factor, right? It's just a number. If E is around 3, 3 cubed is just a little bit less than 27. And that's x to the first. So that is a line. The graph of that is a line whose derivative and slope are the same everywhere, namely E cubed. If that were 5x, the derivative would be 5. If that were 10x, the derivative would be 10. It happens to be E cubed x. Its derivative is E cubed. So just because it has an E in it doesn't mean that it's going to be necessarily a variable function. Make sure you look for the x in the exponent. So I could try to trick you. Now, if you wanted to, you could have done the product rule, remember? You could have done that. The derivative of E cubed is 0 times x goes along for the ride, plus E cubed goes along for the ride, times the derivative of x is 1, and you still end up with E cubed. So as long as you're doing the right thing every time, if there's multiple ways to do it, you should get the right answer. Sometimes you just take a little bit more of a scenic route to the final answer. And if it's Sunday and you're doing homework, hey, that's what Sundays are for, scenic routes. Do a problem in 5 pages instead of 1, right? Only on Sundays. But there is merit in efficiency. Mathematicians do like to be efficient. So if there's more than one way to do a problem, you do want to find the most efficient route. And that's a win-win situation, right? Less likely to make careless mistakes with fewer steps, but you're also getting done faster, which frees up more time for more math. Yeah, win-win. The gift that keeps on giving. All right, we'll stop right there for today. You have a lot already. You could probably finish your worksheet tonight if you wanted. We may finish tomorrow. We'll see.